Hi, my name is Nabil, and I'm one of the team members of Team 8 for our AE 6372 class. We are presenting a reusable hypersonic vehicle. This is a really new, interesting, exciting piece of technology, and it's pretty groundbreaking, so we want to try and present the systems engineering framework and the initial ideas and concepts behind what a platform that's like this could look like. So we'll go ahead and get started. This is just the four of us that worked on it. There's me, Nabil on the left, and then the other engineers, Clint, Ricky, and Nico. So here's an introduction to the concept. The entire idea is to perform a conceptual design and a mission layout and initial systems engineering layout basically for basically a drone that's Mach 4 capable, and it's designed to be unmanned. But the cool part is that the requirements from our stakeholders state that it needs to be able to take off and land from any U.S. naval operated vessel, and it needs to be able to land in open water too, which is already a really tough requirement to make it carrier capable. And then on top of that, it needs to be refurbishable on the order of days. So these are two extremely technically challenging hurdles on top of the fact that hypersonics is still, or even high Mach numbers, not necessarily hypersonics, but Mach 4. These aircraft in that speed regime aren't as common as they should be, and they're going to get more common in the future, but right now the technology is still pretty nascent. So we have it in our high level concept that this aircraft must be robust, easily refurbishable, it has to operate from a naval vessel, and it has to have competitive operating economics through simple refurbishment procedures, because the entire idea of it being refurbishable is that the idea is to lower the sustainment cost. And because it's Mach 4, it should have a high survivability over enemy territory. This thing needs to have the ability to surveil enemy territory and take high resolution photos and scan. So that's the entire kind of mission statement for this. Who's interested? Who are the biggest stakeholders? So I kind of alluded to this already, but this project is basically being built entirely for the U.S. Armed Forces. The U.S. Navy in particular, because it's going to be taking off from naval vessels and it might land in open water, the U.S. Navy derives authority over that vessel, and as such, they're probably going to be a huge stakeholder in wanting to dictate the performance of the aircraft. NAVAIR, which derives responsibility for naval aviation assets, and they're the engineering branch, so they're probably also going to be very interested in how the aircraft performs. And then, of course, you have the other government agencies, the U.S. Air Force, of course, the CIA, FBI, whoever might want access to the data that such a surveillance drone might provide. So these are kind of the big three stakeholders that we've been working with. These are who we derive our requirements from and have our technical meetings with. So the current state of the art, I also mentioned earlier, hypersonics is still a pretty nascent technology, Mach 5 and above. This is Mach 4, so a little bit less than that, but it's still kind of new territory. A lot of the advancements in hypersonic tech that we see today, it's a lot around missiles because they're not easier to design, but they're a simpler design than an actual unmanned aircraft with a payload. Unmanned hypersonic vehicles, they're considered to be like the next paradigm shift because we're simultaneously seeing that we're moving towards more digital engineering, digital future, unmanned, and then combine that with hypersonics. So it's a really exciting paradigm shift. And then I've listed a couple of concepts that are in development by various companies right now. So we have the SR-72, a pretty well-known example of a hypersonic reconnaissance aircraft. I think it's optionally manned, but I'm not sure. But this is being developed for the Air Force. Maybe that's what it looks like. We don't know, but that's one of the concepts. Another thing that we've thrown in is the SNC Dream Chaser because this is a hypersonic capable reentry vehicle, but it's also designed to be easily refurbishable and reusable. And then another kind of intersection of what we want the system to be able to do. The X-51 Wave Rider is a good example because it's robotic. It's designed for Mach 5. I think our product will have roughly the same proportions and characteristics as that due to the nature of the mission profile and the fact that it's unmanned and it has to be refurbishable. So these are three pretty good examples right now of what the current state of the art of hypersonic tech looks like, both manned and unmanned. And then also note that a lot of the development in this area is under secrecy and it's under classified programs. So as that we know of, these are some current examples. So our competitors, since there's no real refurbishable hypersonic naval-based drone that we know of. There are some competitors we can look at specifically for the ISR role, which this is being designed for. So there's the traditional platforms, like on the right you see the RQ-4 Global Hawk, that's persistent surveillance and it's unmanned. Then there's also the U-2, which is high altitude surveillance and then also tactical battle space awareness. That's manned. And then you have kind of the alternate solution to this entire problem, which is satellites. That's an example of what the KH-11 spy satellite might look like. It's a very highly classified program, but obviously it's designed to be able to give you intel on hostile territory. So there are in production options that, as I've mentioned here, but none of them are necessarily designed to meet the requirements that we've been given. The closest thing that we could come up with that's no longer in production, but it still kind of meets, it's still kind of similar, was the SR-71 Blackbird, because that's a high Mach aircraft. It is manned, but it's designed specifically to take high resolution images and do surveillance over enemy territory. So that's kind of a historical competitor that we used as a benchmark against our studies. And then, yeah, just another caveat, no publicly known design exists for what we're exactly trying to do. So this is really a new thing that we're doing. This is really pushing the boundaries of what's even technically possible. So that kind of makes this whole project pretty exciting. And yeah, I'll let Ricky take it over from here.
Hi, I'm Ricky Mackey, and I will begin with defining the problem this system solves, starting with its goals, objectives, missions, and constraints we set. So the goal of this system is to perform a U.S. Naval reconnaissance operation mission, and the objective is to use its high hypersonic speeds to be able to pass through an adversary's territory, avoiding any intervention by such an adversary. So it can use those hypersonic speeds to increase the survivability and the likelihood it'll successfully perform its mission. The mission of the system itself is to survey an adversary's territory in order to gather and provide any reconnaissance or surveillance data that is required. And constraints on the system is that it must be launchable from air or sea. It must sustain that hypersonic flight, so a Mach number of 4 or higher, while it's over an adversary's territory. It must be an all-weather system so that weather does not affect the ability to conduct its operations. It must be recoverable at sea and also refurbishable at sea with a maximum refurbishment time of 3 days so that operations can be continued without returning to an operating base. So the concept of operations for the system you see on the bottom right. It starts out on a U.S. Navy vessel, and then it launches and it flies to the area of operations. While it's over an adversary's territory, it maintains that Mach 4 number, and it conducts that reconnaissance and surveillance operations. Then it egresses from adversary territory, and it flies back to its recovery point, lands on either a U.S. naval vessel or just in the water itself, and then is recovered from its landing point and refurbished for future operations, and then it starts over at the bottom right again. So the functional decomposition of the system is decomposed into 5 main functional phases. So first, the vehicle is launched, then it flies to the combat area, performs its surveillance missions, performs the recovery flight, and egresses from the combat area, and finally it's returned to a launchable condition. So here you can see on the bottom, there is its main function at the top decomposed into those 5 main functional phases. And the further decomposition will start with the first phase, the launch vehicle. That's decomposed into pre-flight operations and then an initiate of the launch. Next, after launching, it flies to the combat area, and that's decomposed into aviate, navigate, and communicate operations performed as it's conducting that flight. Then it performs its actual surveillance mission, so that includes flying at the Mach 4 number and also conducting the surveillance operations itself. Then it performs the recovery flight, egressing from the territory back to its recovery point, and that begins with navigating to the recovery point. It prepares for landing, conducts the landing itself, and finally waits for recovery. And finally, returning the vehicle to launch condition is decomposed into locating the vehicle, retrieving the vehicle, and refurbishing the vehicle. And then now you can see the functional flow block diagram. This is the high-level block diagram, including the 5 main functional phases conducted in order. And then after that final return vehicle to launch condition function, it loops back to the beginning and starts over. Here's the FFBD for the launch vehicle function. It performs all those pre-flight operations in parallel until it's ready to launch, and then it conducts that launch sequence. Next, it is flying to the combat area, and it performs that aviate, navigate, and communicate functions, performs all those in parallel and continuously until it reaches the combat area, ready to begin its next function, and that is performing the actual surveillance mission. So it sets its thrust to maximum to achieve that Mach 4 number, and then it adjusts its thrust to maintain Mach 4 while also following a pre-planned route and conducting their surveillance data. And then once it's done with its surveillance mission, it egresses and performs the recovery flight, and that begins with navigating to a recovery point, conducting approach operations in parallel until it's ready to land, conducting a landing sequence, and then preparing all the systems to wait for recovery. Finally, returning the vehicle to a launch condition begins with locating the vehicle, then retrieving the vehicle from water, downloading any important mission and payload data, and then conducting maintenance and inspection operations until it's ready to be launched, and then all the systems are reset for the next flight, and it begins that sequence over again with the launch. Here's the physical decomposition of the system into its 6 main subsystems. First is the aerostructure subsystem, which includes the structure of the aircraft and any aerodynamic structures. That includes control surfaces as well. There's a payload subsystem to manage the payload. There's a thermal protection subsystem to protect the vehicle from the high temperatures it experiences due to drag at a Mach 4. Then there's a guidance, navigation, and control subsystem, a communication subsystem, and finally the propulsion subsystem, which includes both the engine and a fuel management subsystem. And now I'll turn it over.
All right, thank you, Ricky. So my name is Clint Shirk, and I'm going to be starting off by going through some of the top-level requirements for our system. So you'll notice in many of our system top-level requirements are focused about efficiency and performance. We're really putting a lot of thought towards gaining the most amount of data collected per dollar invested in this vehicle, and you'll see that in many of these requirements. So starting off, we have 6,000 kilometer range. We want to be capable of launching from current infrastructure. We don't want to have to reinvent and redesign and build new launch platforms. We want to use as much of the existing infrastructure as possible to keep cost and build time down. Next, we have recoverable at sea and refurbishable at sea. We're going to be able to recover, refurbish, and launch this vehicle anywhere in the world by naval vessel. This is going to be a huge advantage over many other vehicles of this type. Next, we are flying at 25 kilometers of altitude. We have a turning rate of 20 times the force of gravity. This is a big maneuverability advantage. We want to be able to outmaneuver any other vehicles that might be trying to in pursuit of our vehicle. Next, the system will be following a designated route and capable of receiving commands after launch, whether we have to change route or perform maneuvers to avoid enemy intervention. Next, we have payload capacity of 500 kilograms with a payload diameter of dimension of 2.52 meters by 0.305 meters in diameter. The system has a Class A failure rate of 1 per 100,000 effective flight hours. We have a rate of unplanned detonation of less than 1 in 106. This is to keep our personnel safe while refurbishing the vehicle. and while the vehicle is in storage. Next, the system must be capable of flying through any weather type. We don't want to be limited to only perfect weather conditions. We want to be able to fly through storms and rain and things of that nature. Next, cost development must not exceed pre-allocated budget. Thus, each system must not exceed $20 million and must be in operational condition within 5 years. System must include range safety subsystems. This is in case of control surface failure or AI failure or something of that nature. We want to be able to safely ground the vehicle or safely operate and handle failure situations. So next we have we have to be able to destroy sensitive information to keep just in case we were to ground the vehicle in adversary territory. We don't want sensitive information to be falling into the wrong hands. Next, the system must be capable of remaining operational while in storage for up to 1 year with minimal intervention while in storage. So next off, we have priority metrics. So our top priority is maximum possible surveyed area. Second, survivability or combat loss per flight hour. Next is average refurbishment time. And we have accident rate, which is non-combat losses per non-combat flight hour. This would include while flying to and from adversary territory or the outside of the dash zone. Next is refurbishment cost and unit cost. Next off, we have a morphological matrix. Some of our concepts and alternatives. Starting off, we have a thermal management subsystem with passive. Our options are passive or active cooling networks. Passive cooling network would be simpler and possibly lower cost, but less effective than the active cooling network. Active cooling network's more complicated, more moving parts. We had to use some sort of a working fluid, but it could have better results overall. Next off, we have a structures material type. This includes aluminum alloy, titanium alloy, or a composite. And next we have propulsion systems. The overall propulsion types available are pulse jet, scramjet, ramjet, or solid rocket engines, with fuel propulsion fuel types being JP4, methanol, LP, liquid propane gas, or solid fuels. Next off, Nick will be going through and weighting some of these alternative options in a TOPSIS analysis. All right, thank you.
All right, thanks, Clint, for those alternatives. And now we're going to go ahead and use TOPSIS to evaluate those alternatives. And we'll talk about why we use TOPSIS in a second. But first, I'll go over the actual methodology. So first, we took those alternatives that Clint just went over and evaluated them against criteria. So we have speed, range, payload, acquisition cost, lifecycle cost, durability, longevity, and safety. And these are all kind of in line with most of our requirements. And each of these were evaluated on a 1 to 9 scale. So, for example, a scramjet being faster than a ramjet gets a slightly higher score, but it being such a high number and able to surpass the requirement, it still gets quite a high score. The ramjet would still get quite a high score. So each of these were evaluated with this certain number, and then in the second table we can see that those numbers were normalized, and then in the third table they were weighted. So we weighted speed and range as the number one. Basically, they were twice as important as the rest of the evaluation criteria, and this is just because that those are really the most important, and they need to be met for the requirements to be met and for this entire system to make sense. So once the weighted values were evaluated, the ideal values were selected for each section and subsection, and the differences from those ideals were found. So the max differences, so the differences to the ideal and the differences to the worst were found, and then in the bottom table the addition of those was calculated, and the result is the highlighted in green alternative. So the ramjet was selected, the composites as a structural material was selected, and then an active cooling system was selected. And this makes sense. Ramjet is right around the speed we need without too many drawbacks. Composite materials are light but strong, but heat resistant, which is great. And then active cooling will likely be needed. So why did we choose Topsys? Well, there are multiple options for this trade study. AHP is overly complex for our stage right now. That would require much more knowledge of the system and further analysis. Decision matrix, on the other hand, is too simple. It doesn't take into account enough, especially relative importance, just like the Pew matrix. And with that as well, it's difficult to assign a baseline. The Topsys does allow us to assign relative importance. And then on top of that, it's dependent on weighted values, which can be a disadvantage. But the weighted values in our case are very easy to assign. It's very easy to know, which propulsion mechanism will be faster and have a higher range. It's very simple to know, okay, aluminum is cheaper than composites, but it's clearly heavier and has other drawbacks as well, like heating compared to titanium. So Topsys outputs a clear winner for us, and the winner is based on weighted values that are quite easy to assign. And then finally, the complexity is just right for the current stage. So that leads us to our concept. So our concept would basically look like one of these three pictures shown, and basically low profile, low drag profile with no wings, no tail, fins for control with a ramjet in the front. And then the final interesting feature would be the size. So our range is much larger than most concepts currently. So the dimensions would have to be much larger, and that's a sizing problem that would be the next stage in our analysis. So to verify our requirements, 4 techniques are available to us: inspection, analysis, demonstration, and testing. The majority of our verification will be through demonstration. For example, launching from a naval vessel or aircraft, being recovered, being refurbished, its altitude, flown, being able to follow a designated route, receiving commands, carrying a payload. All that stuff will have to be demonstrated, as well as its self-destruct system. A demonstration will be in order. As far as testing, G-force tolerance will have to be tested with actual equipment. Failure rates, safety, weatherability, capabilities, storage capability all have to be tested, because 1 year of storage cannot be demonstrated. A couple of analysis will have to be made. The range will have to be analyzed to see if it hits that range based on other tests. The cost and the time to initial capability will have to be analyzed and predicted. And then things like the dimensionality, whether or not includes a range safety subsystem, and the pre-allocated budget, all just are inspected to verify. Now moving on to the risk matrix, we looked at the most common risks and most likely to impact our concept. And as we can see, most risks are in the yellow range, but the highest risk here is number 2, the technological readiness, and this is just because this is a unique vehicle. Nothing out there exists right now like this, and hypersonics are relatively new. So we recognize that the technological readiness is the highest risk. The next one would be a cost overrun, just because of the nature, the complexity of the design. However, these both can be planned for and prep for adequately. So in conclusion, hypersonic technologies are the future of defense. Right now they're being worked on by almost every superpower in the world. The US is no exception. And our concept brings capabilities that currently do not exist anywhere else. Our concept can improve on the current capabilities of, for example, the U-2 or spy satellites or something like the SR-71. It directly meets needs that those competitors just cannot and do not address. And so for that reason, we think that our concept is a fantastic concept for the future of ISR. And we think it has high feasibility and technological readiness with only manageable risk. So that concludes our presentation. Thank you so much for listening. Let us know if you have any questions. Goodbye.